Thank you very much for that introduction. Good morning, everyone. I'm Ben Usage from the University of Illinois at Urbana-Champaign, and I will be presenting my work completed with my colleagues at UIUC, MIT Lincoln Laboratory, Princeton University, and Northeastern University on cross-app poisoning in software-defined networking. So to give a bit of a brief background, particularly with terminology, software-defined networking differs from traditional networking in that rather than having decisions about forwarding and rulemaking be a distributed decision, SDN tries to centralize that into a logically centralized SDN controller. This controller acts in some ways as a network operating system that controls what is termed the control plane of the network. The control plane makes decisions, and these get actuated in the data plane as flow rules that allow end hosts to communicate with each other. So this network operating system then is extensible in the sense that we can expose a shared SDN control plane state made up of different data structures from which different networking applications or apps extend the functionality. These applications communicate with the SDN controller through what's called a northbound API. So some example applications include, for instance, firewalls, load balancing applications, and routing applications. So there's been a lot of interest in recent years, particularly as SDN relates to security, in using SDNs to improve end host security. So for instance, fine-grained access control or monitoring for intrusion detection systems, SDN allows you greater insight into what's going on with the end host in your network. At the same time, though, we should also consider the security of the SDN infrastructure itself. So while SDNs have been used to improve end host security, through these flexible policies, the security posture of SDN itself must be considered. So an article from IEEE Security and Privacy Magazine from last year noted that attacks against SDN controllers, and in particular malicious controller applications, are probably the most severe threat at the moment to software-defined networks. What makes this problem even more complicated is that there are dynamic configurations that can be now implemented through these applications that make it difficult to understand for practitioners of a network what's actually going on in their system at a given time. So from this, we see the need for greater insight into the decision-making that went on among these different applications to then create the state of what the network looks like at a given time. At the moment, most SDN controller implementations use role-based access control in the control plane as the current state of the art. The challenge, well, before I get into the challenges here, one way that this is implemented is that you have various network applications that are granted permissions to work on different objects within the control plane. So in this example, I have a very simple SDN controller that manages host and manages flow rules that dictate what the forwarding policies actually do in the network data plane. And I have several applications here that I've granted permissions according to an RBAC policy. So for instance, we have a malicious application A1 that can read and write to the host data store through the host manager of this controller. And I also have a host networking application that can not only do host reads and writes, but also can read to and write, or read from and write to different flow rules in the network. And so we see here that the malicious network application can't directly write to the flow rule manager to affect flow rules in the data store, to affect eventually what happens in the SDN control plane. The challenge here, though, is that malicious applications could potentially influence other data structures that other applications then can read from without having permissions to do so itself. We see here that role-based access control is insufficient because it does not track information flow. And so why this matters in particular for SDN's case is that the SDN architecture generally does not include inter-process communication and, in most cases, sandboxing. All of these different applications read from and write to the same shared SDN control plane state. So this makes it even more challenging to understand the information flow request among different apps as they influence what happens in the control plane. So the approach that we've taken to try to mitigate this problem is to basically track information flow within the SDN control plane. And in order to do that, we try to formalize the problem as we term it cross-app poisoning. So it's the information flow control integrity problem for SDN control planes. We want to formalize it and understand the extent to which this actually occurs in practice. And to do that, we take a role-based access control model, find out which applications can read from or write to the different objects, and then perform static analysis to find out where these data flows actually occur between different applications. So by being able to do that, we can then enforce information flow control over these different applications using an online reference monitor. And to do that, we apply data provenance techniques to track information flow and enforce information flow control, ideally with minimal latency. And we create a system called PROVSDN in order to serve as that online reference monitor that not only interposes on all control plane communications, but then makes a record of what happens for after-the-fact analysis as well. Throughout this paper and presentation, we use the ONOS SDN controller and its security variant called Security Mode ONOS as our case study. So before I begin, I'll explain the threat model a little bit. We assume that an attacker here wants to arbitrarily install flow rules into the network to affect data plane connectivity. In being able to do that, they can allow different end hosts that they might control on the network to be able to communicate with each other, for instance, to do lateral movement attacks. So if an attacker can install flow rules, then they've now used the SDN as part of the attack surface to their overall campaign of what they want to accomplish. From the defender's point of view, they want to prevent these cross-app poisoning attacks even after role-based access control has been applied. We make several assumptions here about the system. First, that the SDN controller itself is trusted and adequately secured. I should be careful to note here that while we assume that the data structures that live within the control plane may be tampered with by different applications, some malicious, some not, these applications aren't necessarily going after the controller code itself. So we assume the controller and any components that we add onto the controller for provenance purposes are adequately secured. We further assume that apps may originate from third parties and are then therefore untrusted. There are several cases where different networking applications have, or different SDN controller ecosystems have app stores that people can download third-party written applications that can then talk to different components of their network to either get information out of what the network is doing or enforce some kind of policy in the network. Finally, we assume that the attacker controls the least privileges apps. So we assume that the practitioner enforces least privileges access control in the network so that the applications can at least perform minimal functionality that they need to be able to perform successfully. We should be careful to note here that not all information flow is bad. In particular, some information flow between different applications may actually be desirable. However, current SDN solutions at the moment don't allow practitioners to differentiate between the cases of what's desirable and what's not. So give a brief explanation about what cross-app poisoning actually is. It's the information flow control integrity problem for SDN. And so essentially here we're trying to figure out which applications are influencing which other applications. To do that, we start with a role-based access control policy model that we have. We look at different applications that live within the control plane, different objects that live within the control plane as well, and read and write permissions that these different applications can read from and write to these objects. And then from that, we produce a graph essentially that shows the connectivity among all of these. To the right here, you see that we assign different semantics to the edges. So for instance, an object to an app implies that there's a read permission by that app. Conversely, if it's to the object, it's a write permission. And our goal here is then to find these paths from apps to objects that are not directly connected. If they're directly connected, those would be the permissions that the apps would have otherwise had. But we want to see what influences that these apps have in terms of connectivity. So you see the example on the bottom right is essentially what we showed earlier in the presentation of a malicious app trying to influence, in this case, object 2, which it does not have direct access to do. We applied these techniques over the ONOS system, including there are about 60-some applications that are included with the ONOS code base, and they require different permissions for enabling the security mode ONOS to work. The large dots here represent the applications. The small dots represent objects or data structures in the control plane. And we found that there is relatively strong connectivity that potentially shows highly dependent data among each other. We ran a shortest path algorithm over that graph to find that most apps could either directly or via one other app access different objects within the control plane potentially. However, this is not necessarily a complete picture of what actually goes on, because we now have to consider that writes may not always causally depend on reads. So to narrow down the actual dependencies, we had to perform static analysis over the applications themselves. And to do that, we performed field-sensitive interprocedural data flow for static analysis in order to identify what we term cap gadgets. Essentially, cap gadgets are programs that allow a flow from some permissioned data source to a permissioned data sink. And in the example that I show on the right, this comes from a basic learning switch forwarding application that's included in ONOS that shows that a source that requires a permission here is a packet that comes in from the data plane, and the information from that packet is then used to write out to a permissioned data sink, which is, in this case, a flow rule. So it's taking information that's read in from a packet and writing out to a flow rule, essentially. We can chain various cap gadgets together, but we assume that the attacker has some sort of a triggering app to be able to start this chain reaction process. So by being able to influence one data structure, they can then propagate what they want further down on the line and use other applications in order to do it. When we analyzed this for ONOS, we found that there are several instances where the sink in this case is a flow rule write. So it requires the these applications require the flow rule permission to be able to write to the network, but other applications can then influence the data structures that these apps that do have this permission read from. And we found several cases where that occurred. In particular, packet reads were also very common. From this, we can deduce that attackers can leverage these other data structures to affect flow rules, i.e. affect what happens in the data plane without having the flow rule permissions granted them themselves. In order to solve this problem, we use a data provenance approach that we build into a system that we call PROVSDN. So for those who are not familiar with data provenance, essentially it tracks how data were used and generated in a system, by which processes did they either used or generated this, and then whose responsibility is it for these processes, in this case, different applications. And we can store these various relations among all of these different objects as a provenance graph that we can then query from. In this case, we used a standardized provenance modeling technique from the Worldwide Consortium's PROV model that we use throughout, and I'll explain a little bit later on. To be able to implement information flow control, we implement a very simple model that has floating object labels and fixed app labels. So we assign different integrity labels to the various applications depending on what levels of integrity we assume that these applications have. And then as these apps read and write different data objects, those inherit the integrity labels that the applications have. The reason that we use provenance in this case is that it makes it very amenable to be able to quickly search for determining what an object's integrity label is, essentially its path connectivity in the graph. To give a brief overview of what PROVSDN actually does, we assume that an external application tries to, or an internal one as well, tries to talk to the northbound API to do something in the control plane. That request gets intercepted by PROVSDN, which collects information about it, tries to create this provenance metadata about the request that gets stored in the provenance graph. Once it's stored in the graph, then an online reference modder checks that the information, whether it follows the information flow control policy or not. If it does, then, and if it's allowed, then the request is handled as normal. If not, we can either warn the practitioner or prevent the information flow from occurring. We implemented PROVSDN in this case on the ONOS SDN controller, though. If you're interested in how it could be done on other controllers, we explain it a little bit in the paper. To evaluate PROVSDN's efficacy, we looked at a simple attack evaluation. So we wrote a triggering app that modifies an incoming packet before being received by, we assume, a forwarding application that essentially allows layer 2 forwarding to occur in the network. So we assign labels here as the trigger application as being low integrity and the forwarding app as being high integrity. The policy that we want to implement is that we want to prevent information from low integrity apps from being able to flow to high integrity apps. And we ran the attack and were able to successfully prevent this. But we also generated a provenance graph as a result of this that is shown on the right. I'll walk through it very briefly. Provenance, you read, basically you go back in time in terms of how you want to read it. So we start at the bottom here in this case of a forwarding objective. Essentially, it's a flow rule that would have otherwise been instantiated into the network. We look at who's trying to install this flow rule, and we see if we go through the relations in the graph that the forwarding application tried to do it. The forwarding application was trying to read from incoming packet that it received. But we see in the provenance graph that this incoming packet was tampered with essentially by the triggering app that we had. And so because we now see a link between the flow rule that we're about to add to the network and the trigger app, because the forwarding application has higher integrity than the trigger app, this should be blocked. And our provenance graph captures all of this information. We tested the performance of PROVSDN using a metric called flow start latency. Essentially what this metric looks at is the time that's required from one end host to be able to communicate with another end host in the network if the SDN control plane has never seen this host before. Generally, it goes to the first switch. Since the first switch in the network doesn't know what to do with it, it sends the request up to the controller. The controller decides what to do, instantiates a flow rule, and then allows the two end hosts to communicate with each other. So we looked at that first packet's end-to-end latency. We found that without PROVSDN, we had about 11 to 12 milliseconds of latency. With PROVSDN, we had about 28 to 29 milliseconds. Now we find that this could be an acceptable latency when amortized over long flows, because this only occurs in generally in the first packet of a flow. So we'll only see PROVSDN have to record and add this additional latency on that first packet rather than for every subsequent packet in the flow. And we see this as a generally acceptable trade-off. So in summary, we analyzed the information flow control integrity problem in SDN control planes by investigating and being able to observe information flow among these different applications. We proposed a model to identify these interactions that apps have through the shared SDN control plane state as vectors for potential attacks and found where they existed in practice using ONOS as a case study. We proposed a data provenance approach that we then implemented with our system called PROVSDN to record this control plane state evolution and be able to enforce through an online reference monitor information flow control in real time. And finally, we implemented this in the ONOS controller in particular. So I can take questions now.
If you have questions, please come to the microphones.
Hi, Lorenzo Di Carli, WPI. I think it's very interesting work. I'm just curious. So it seems to me that you consider the existence of an information flow as a potential security issue, right? Mm-hmm. I was just curious if you actually looked into the semantic of those CAP gadgets to see whether, for example, an attack application could perform anything of consequence to the net. So let me rephrase. It seems to me that the existence of an information flow is a potential security issue, mm-hmm. but I was wondering if you look at the potential concrete attacks that an application could carry with this system.
Right. So being able to influence the packet, in this case, we used a packet. Excuse me, sorry, I'm just going to plug in. Oh, sure.
Go ahead.
Sure. Yeah. So we could, in most of the attacks we found, we looked at packets that were being read from this application, then flow rules that were being written to. And we found that being able to write certain things, basically being able to tamper with the incoming packet, allowed us to do, for instance, denial of service attacks in the data plane. So I think, is that what you were going after?
Yes. Okay, yeah. Thank you very much.
Yep.
Thanks, Jianfeng from China. And I actually encounter a real problem like this, and but my problem is much simpler. And I want to ask if there is a third-party program. So if we don't have the source code, how do we do? Yeah.
Right. We would have to do some sort of binary analysis. So in this case, we're lucky that we had the source code available to be able to understand where these attacks occurred. Even if you don't necessarily have the source code available, if you run, say, a black box in your system, black box application, and enforce provenance over that, you can at least see if it does occur, what it's actually doing. So you may not be able to write a policy initially to know ahead of time that these shouldn't be able to communicate, but at least if they do try to do that, you can see that in the provenance graph.
I mean, okay, I see. Thank you.
So very nice work. Okay, my name is Gofei Gu from Texas A&M University. So the approach is very nice and seems that it's pretty generic. I can see that that's not applied to, let's say, mobile phone or PC or any computer, right? So in your case, can you tell us, is there any specific challenges that you see or specific to SDN that you encounter when you are building the system?
Right. So I think a close comparison might be the Android operating system, in that it has a very, at least for Android, a very broad app ecosystem. What we found that, in contrast to, say, Android or traditional traditional operating systems, is that there's no notion of inter-process communication. So apps to be able to talk to each other had to go through the control plane in order to do it. That may be an architectural limitation with the SDN design, but that's essentially how it works in the present day. And so we found that to be rather challenging, because this now allows any application to be able to influence what happens to other applications. And while we could say that, if you had more permissions, more fine-grained permissions, maybe you can mitigate the problem to some extent, but you'll also have applications that, by necessity, have to influence everything that happens in the network.
So I actually have a question. So with provenance approaches, one of the issues is oftentimes the provenance graphs can become very large. I was wondering if you could tell us a little bit more about what these graphs look like, and say how much, for example, storage you might require for a system like this.
Right. So we did notice in testing that there was a lot of provenance graphs being generated, or the provenance graphs could get rather large. We were able to fine tune it to some extent to be able to say, so like if there were internal controller activities that we weren't necessarily interested in, we were able to turn those off and actually generate a lot less provenance for the problem that we had. Okay, so it's something that you could configure based on, say, your application, or I had another question, actually, and I was curious. So the work is predicated on being concerned with malicious applications, and I was wondering if you could maybe tell us a little bit about how these applications come to be, and what kind of threat are we really concerned with these apps? Are we talking like someone who's very sophisticated, or is this an attack that anybody could do? So for ONOS, I can speak to that. So that there are like 60 applications included in the repository for ONOS. So essentially any third party can contribute. And if they get it accepted by the ONOS community, then it becomes part of their code base. So yeah, take that as you will. Okay, so anybody can contribute these, and all bets are off as to how secure they are. Yeah. All right.
Yeah, who's responsible for assigning integrity?
We assume a network or security practitioner based on what threat models they assume. So for instance, if they have a third-party application that they're trying to install in their network, they may initially say it's a low-integrity app because they don't necessarily know what exactly it does. So they might want to say, apps that we've vetted properly might be high integrity, and then any other apps that we want to test in our network may be low integrity.
Thanks.
Okay, well, let's thank our speaker.
Yes.